to just your basic trig stuff. We did a little bit of the idea of how to find the missing side lengths, given that like cosine of theta was 5/7. We knew that that was the adjacent and the hypotenuse, so you're going to use Pythagorean theorem to find the missing side length and all that kind of stuff. Well, we kind of do that again today, but instead of saying that the cosine of theta is 5/7, I'm going to give you a set of ordered pairs, and you're going to figure out all the trig functions via the ordered pairs. In doing so, what will happen is that you're going to also be able to start to see of the importance of what we've been talking about, the whole idea of that reference angle, how far off something is from the x-axis, why are those important, and how things are moved via ordered pairs. You'll also notice when we do our ordered pairs, there's an x value and a y value. Well, those are going to correspond to specific trig functions.
Never heard of again.
All right, so when you start with this, if we have if we start with something like this, where we have our x, y for our ordered pairs. Yes, ma'am.
Should I write this really big, like this?
No, we're not doing the whole thing. I'm just talking about the quadrants. What's positive where, what's negative, and all that kind of stuff. Okay. When you have quadrants, your four quadrants, each of those has specific signs, SIGNs, for them. For example, first quadrant, x and y values are both what? Positive. Second quadrant, it's negative x and positive y. Third quadrant, they are both negative. And fourth quadrant, it's positive and negative. We also know that if we put any ordered pair in any spot, it has some corresponding x value, y value, where the x is the distance on the x-axis, y is the y value, which generates a hypotenuse. In this case, we're going to start calling the hypotenuse R. Okay?
Because that's the radius?
Yeah. Okay. And that's where this comes from. Now, if you start to sit there and look at it, if I draw it like this, that places theta here. Remember how we were doing that? Theta comes up off the x-axis. So that's coming up off the x-axis. What's the cosine of theta going to be in terms of x's and y's and r's? What is it? Cosine. X over r. Sine. Tangent. Y over x. So what we're going to start to do here is your ordered pairs will generate specific values from into a right triangle by being able to do the cosine of theta is going to be x over r. I'm going to put them in this order, cosine, sine. I know it's weird that we say cosine, sine, because we're so used to saying sine, cosine, tangent, SOHCAHTOA. If you look at the buttons on the calculator, it goes sine, cosine, tangent. But I want you to see why I'm doing it this way. And we just said tangent was y over x. What comes first in the alphabet, x or y? What comes first in the alphabet, cosine or sine? Cosine. Cosine is your x value, sine is your y value in an ordered pair. We'll get there. It starts to get real crazy. What's the inverse trig function of cosine? And destroy it. Metallica reference, seek and destroy. Cosecant is r over y, and cotangent. Reciprocal functions. They can split. You have to look over.
I'm memorizing.
Very well. Now, what's nice is that you don't necessarily have to do that. Because once you place a theta, doesn't matter where it goes. If theta winds up being in the third quadrant, for example, oops, wow, that's really badly drawn.
Not drawn to scale?
Not drawn to scale. If your theta takes you to the third quadrant, that reference angle that we've been talking about is the angle coming back up to the x-axis. Remember that? So if I had something like this, that would mean theta would have to be placed there. If this is still some value of x and y, I had to move down some y value, I had to move left some x value. What's negative x quantity squared? It's just x squared plus y squared. It's still going to equal r squared. So you still get the same radius no matter what, even though because of the Pythagorean theorem. So when you have that the idea of that reference angle, as things move around, it's always going to help generate where your ordered pairs move. Yeah.
I'm gonna use that like pi over.
We're getting to it. We'll probably start that tomorrow. Okay? And it all comes back with the whole reference angle. If we understand how to set up the reference angle and find the right reference angle, after we start to build the unit circle via the special triangles, it's really easy. It sounds awful in your picture, but as long as you know the ratios of your sides of the special triangles, you don't have to build the whole thing. You just have to know what the values are. So what happens then, let me just wrote all this out. Yes. I can take an ordered pair, 3, -4, and when it says be on the terminal side, that just means where theta spins to. So if I have the ordered pair 3, -4, and I'm going to list out all 6 of my trig functions. First thing you have to do is just place it. What quadrant is 3, -4? Fourth quadrant. So we draw it. It's right there. So theta comes spinning around here. And the reference angle that's created is right here. The reference angle is what takes you back to the x-axis. Okay. That reference angle is looking at the y value or the x value? It's looking at the y value, isn't it? Because the y value is the vertical part. It happened to move down -4.
Is that always going on with the y?
Yeah.
So basically theta will always be inside your triangle?
Yep. Because we always place theta as the reference angle. The reference angle is always what it takes to get back to the x-axis. So no matter where you wind up being placed, if you're down here, theta comes back up. If you're up here, theta comes back down. Yes, sir. Oh, sorry, I thought you had. I put my eye, I thought you had up. So, yeah.
So let's say like you're being heaven at 2 1/4 of pi. So like if you had to go back, would it still just be like if you have more than one rotation?
You still wind up in there, but what's going to happen here, you don't have to worry about rotations with these things because they're just talking about this is the spot.
Yeah. So the circle doesn't matter?
No. No. Yes, ma'am.
So you just be solving for the triangle?
Pretty much.
Like
Here's-
you can find the
Yeah, yep, we're getting there. So I'm looking at the -4, that's my y value. My horizontal one was my adjacent, and that's 3. What's my radius? 5. 3 squared plus -4 squared is 25. It's one of those silly triples, isn't it? Yeah. So it's 3, 4, 5. So now, it's just, what's it?
Is it not negative 5?
What's -4 squared? It's positive. Can you ever have a hypotenuse that's negative? Because what happens is, no matter what, whenever you place this, because you're going to square your negative, your distances will always be, when you do that, the distance is still positive. Because the -4 just means it moved down 4. From 0 to -4, that distance is still 4. It just went a different direction, that's all. That's the only difference there, okay? Hey, does that make sense on that? So you have a radius of 5, and now you just go through your trig functions. Cosine is x over r. Well, what's that? 3 over 5. So once you start to place this, just like Hopworth was saying, a lot of times you're just solving out the triangle for the 6 trig functions. It's just a matter of placing it in the right quadrant so you know which ones become positive and negative. Your sine is your y over r, so this case is negative 4 over 5. Tangent being negative is y over x for opposite over adjacent. And that's a negative 4/3. What do you do for all the reciprocal functions then? You just flip them. Exactly. All you have to do is just flip them. So the reciprocal of cosine is secant. The reciprocal of sine is cosecant. The reciprocal of tangent is cotangent. So we have the secant becomes 5/3. The cosecant is negative 5/4. Does it matter where the negative goes in fractions? And then the cotangent is, what's that, negative 3/4. Okay. It is quite literally so eerily similar to what we did before in that first section where I actually had you guys, I think I gave you a problem before. It was cosine of theta was 5/7. That just meant you drew a right triangle, placed the theta, did 5 over 7, and you just figured out the other side. This, instead of just giving you, because I didn't give you anything with negatives. Yeah, but I didn't do anything weird with that. Here we just move it. We move things around in different quadrants to look at their different signs, the SIGNs. Okay. Nay. Nah. Kinda. There's a little bit more to it. Let's try this. Negative 12, negative 15.
Wait, do you have to write out all 6 functions every time?
Yeah, it'll say right off the 6 trig functions. So if I have negative 12, negative 15, what quadrant does that place you in? Quadrant 3, very good. Both the x and the y are negative in quadrant 3.
Do you always draw like the right angle line straight up, or would you go to the right?
Always go to the x-axis. Because if you always go to the x-axis, that means theta is your reference angle. We never draw to the y-axis. Not that we don't like it, we just don't do it. Why? What did it do to you? Oh, I thought it was Sadie, because she's usually mouthy. Why? Why? What did it do to you? So again, theta, it's looking at the vertical portion. Well, the vertical portion is the negative 15. The adjacent portion, the horizontal, is your 12. What do you do to figure out your hypotenuse? Pythagorean theorem. So 12 squared and 15 squared, it's like 7 years ago. Our founding fathers brought forth, sorry. Was it 144 and 225, 369?
144 plus.
You can do 112 squared.
225 plus.
144 is 369. So if I'm looking at 369, it's kind of obvious what perfect square goes into a 36 and a 9.
3.
Well, 3 words, but is 3 a perfect square? But what's 3 squared?
9.
9. So 9 goes into 36 how many times?
4.
So it's 3 root 41. 41 is prime, so it wouldn't take you long to figure that out. I mean, you'd be able to take out 2 3s right away.
Unless you don't realize that 41 is prime. That'd be a big issue.
That would be a problem, yes. So then you just go through your trig functions again. And bear in mind that you have to rationalize your denominator. But is it really hard to worry about root 41s in the denominator? No. So go through your list. If we start with cosine. Cosine is x over r. What's your x? Your r is 3 over 3 root 41, so it's negative 12 over 3 root 41. Well, to rationalize that, you just multiply top and bottom by the root 41. Do you agree?
Yes.
What's negative 12 divided by 3 then? 4. So you get negative 4 root 41 over 41. That would be your first rationalized cosine value. Okay. You do the same thing with the sine value. Sine is your y value over the radius. And then we have 5 root 41 over 41. Oops, sorry, negative 5.
Would it be negative 15 or negative 5?
It's negative 5 because I did negative 15 divided by 3. I simplified that first, and I knew the rationalizing part's the exact same as it was just a second ago, so it's just real quick. And a lot of times you'll see that. You really only have to do like one part, and then everything else just kind of replicates itself. Okay. The last one would then be tangent. Tangent is your opposite over your adjacent, your y over x. What's a negative divided by a negative? It's positive. So this becomes divided both by 3, you get what, 5/4, I believe? So, yeah, always, always, always. Always, always, always. Did you notice something in this third quadrant? Cosine was negative, sine was negative, but what was tangent? It was positive. The reason was, if you go back to what we did a second ago at the very beginning, if I did tangent was y over x, what's a negative divided by a negative? It's positive. A positive divided by negative is positive divided by positive, negative divided by positive. So the quadrants tell you what the signs, SIGN, of your trig functions will be. Cosine, positive. Sine, positive. Tangent, positive. All 3 of them are positive in the first quadrant. Cosine is negative. Sine is positive. And tangent is negative. Because no matter what, when you place a theta, this is some positive value, that's some negative value. Tangent will be negative. Third quadrant, negative cosine, negative sine, and positive tangent. Because negative divided by negative is always positive. Okay. And then lastly, in the fourth quadrant, we have positive cosine, negative sine, and a negative tangent. Remember how I was saying when you're working with reference angles, how things, I hate to erase this, it just looks cool.
You could do the other one.
Too far away. Remember how I was saying this before? When you have ordered pairs, if you have the same ordered pair, let's say it's 3 and 5. 3 and 5, 1, 2, 3, 4, 2, 3, 4, 5. It's here. If I reflect that to the next quadrant, what changes? The 3. The 3 becomes negative. If I bring it to the next quadrant, what changes? 5. If I go back here, and you get this, you create a rectangle just by reflecting things around. Well, the reason why that works is because this reference angle never changes. It's pretty close, isn't it? Not bad for me. Because the reference angle never changes, and your diagonals are playing the role of your hypotenuse, if you will. That hypotenuse value always is going to be the same for each one of those as you square it out. That's why that works. Because all of those slopes don't change. Okay. That's why knowing, I think it's all students take calculus. All students take calculus. Which ones are positive? They're all positive. Sine is positive. Tangent is positive. Cosine is positive. Or do you need to bother with that? No. If you know how ordered pairs get placed into the quadrants, it doesn't matter. As long as you know where your quadrants go, you're fine. What's that? Let's see. Which gets us to this. Which gets you to something that most people tend to think is really, really, really difficult, but yet it really shouldn't be. Quadrantal angles. Okay. All right, so your quadrantal angles are the angles that lie the quadrantal angles are going to be the angles that lie on an axis. Okay. Your quadrantal angles are going to be the ones that lie on the axis. Those are 0, 90, 180, 270. Zero, pi over 2, pi, 3 pi over 2, 2 pi. 0, 90, 180, 270, 360. Any one of those, what's the word? Coterminal angles on the 90 degree, every 90 degrees, every coterminal angle, they all would lie on an axis. Those are called quadrantals. On axes, if you think about it, you know one of the ordered pairs. You know one of the values of the ordered pairs. For example, if I'm out here, what's my value of y? If you're on the x-axis, what's your y value? 0. If you're on the y-axis, what's your x value? 0. So I know that if I start here, my y value is 0. Here, my x value is 0. Here, again, my y value is 0. And here, my x value is 0. It has to be because you lie on one of the axes, just by the rule. 0 for y, you're on the y-axis or x-axis. 0 for x, you're on the y-axis. Remember how we did cover and solve before to figure out y-intercepts and x-intercepts? Same basic principle. It's just a little bit weirder, shall we say. Okay. Now, remember last year in geometry how we never worried about finding any of the trig functions of 90 degrees? Well, let me show you why we did that.
Isn't it also like sine of 45 is always the same?
Yeah, and we'll get to that because you're opposite and you're adjacent to the same values. If I'm at 90 degrees, what's my opposite? Hypotenuse. My opposite is the hypotenuse. And what's my hypotenuse? My hypotenuse. So the sine of 90 degrees would be hypotenuse over hypotenuse. It's always going to equal 1. So at 90 degrees, have I kind of given it away yet that the y value is your sine?
No.
Well, your y value is your sine.
Thanks.
You're welcome. What's your x value? Cosine.
Oh, yeah, you said
I did say that. Because what comes first in the alphabet? Sine or cosine?
cosine.
Cosine, what comes first in the alphabet? X or y? X. You're like Q, R, S, T, U, V, W, X!
No, I wasn't starting.
No, I do like W as Y.
So the reason that works is you get that. Now, let me show you something else. If you're using the idea we did a second ago, x squared plus y squared equaled our r squared. You guys okay with that? We did that earlier with the other problems. So, yes ma'am?
Would it never matter for like cosine then? Which one would be your adjacent?
We'll get there. We'll get there. So what happens here, what's your value of x at 90 degrees? 0. What's your y value? 1. So what's 0 squared? What's 1 squared? What's 0 plus 1? What's the square root of 1? 1. So my r value here is 1. So when I'm at 90, my y value equals the r value. What's that? Aren't they all segments though?
Aren't they all equal ones? So it's not like equal
It's not a line to them segments.
It's not, well, I don't want to say it's line because it'd be infinite, but what I'm saying, it just, it has, yeah, that's what I'm saying, that's why we're going with segments. It has 2 ending points. No matter where I place wherever I place that y value, if it's at 7, the radius would have to go from 0 to 7. If it's at 3, it's at half. It doesn't matter because they would always have to equal each other. That's why your sine value is always 1. Same idea as you go out here. When you come out this way, you kind of have the same principle. When you start looking at the cosine of 90, how do you know which one is which? Exactly.
It doesn't matter, right?
It doesn't matter because it has to be
1.
1. Your x value here is going to be 1. So your r value is 1, which means your x and r are equal at 0. Here it's negative 1. Here it's also negative 1. So as you go through at 90 degrees, 180, 270, and 360, or 0 if you will, each one of those quadrantal angles has the ordered pairs of zeros and ones depending upon where they're placed as you go through. So if you had any value, whether or not you spin around, you land on one of the quadrantals. For example, if I want to do 11 pi over 4. I'm sorry, 11 pi over 2. If I wanted to figure out the 6 trig functions at 11 pi over 2, first thing I would do is figure out where does 11 pi over 2 land. And you guys have drawn that the other day. So if I go 11 pi over 2, 2 goes into 11, how many times? 5, and how many are left over? So we spin it, figure out where you land. 1 little, 2 little, 3 little pies, 4 little, 5 little. Where do I land? Here. What's the ordered pair there? 0, negative 1. Which means I can go through and list all 6 trig functions at that value. Cosine, sine, tangent.
Well, they only see 1.
Nope.
Can you scroll full time?
Yeah. Let's bring this down so everyone will work. Is that all right?
Yeah.
What's the R value when you're on the quadrantal? No matter where you are. It's always going to be 1. Your R value is always going to be 1 whenever you land on a quadrantal, no matter what. Your R value will always equal 1. So in this case, what's my value of x? 0. So the cosine at what winds up being 3 pi over 2 is 0 over 1.
Sine is -1. Okay.
And that's where all this comes through.
Yeah.
Okay? The sine is going to be -1 over 1, which is -1. Tangent is -1, or excuse me, y over x, which is what, -1 over 0, and then can you divide by 0? No, so what do you say it is? No, you say
Not
undefined.
possible.
Say it undefined.
I think you just write
If we just wrote no for that on a test, would you say?
It has to be, technically it's called undefined, okay? Look at this whole time. You're just taking Jory's spot for today. No offense, Jory. We miss you.
Yeah, I'm sure she
She's
heard
a
that
lot,
word.
60-degree and
I am recording this, so they can watch it later,
Oh.
but she won't. So now, what's the inverse of cosine?
Secant.
Secant. What's the inverse of 0?
No.
0 over 1 becomes 1 over 0, so the inverse of 0 is undefined. Remember how you did slope stuff? How you did inverse, opposite reciprocals and stuff like that with slopes? The opposite of a 0 slope is an undefined slope. The opposite of an undefined slope is a 0 slope. Same basic idea. So if I do cosecant, oh, I'm sorry, secant first. That's your r over x. So you flip that, you get 1 over 0, which is undefined. The cosecant, what's the reciprocal of -1? -1. And then the cotangent is x over r. So what's the reciprocal of undefined? 0. That's what you're being able to do when you're laying out quadrantal, because you know your ordered pairs. As you start getting through more and more and more of these, the whole idea of how these things are spun around allows you to figure them out. Okay?
Yay.
Quadrantals, for some reason, always tend to get a little messy. But just remember, you have, there's only 3 of them. And all the rest of them all just co-terminal. Because no matter what, you're still going to, if you spin and you wind up on that ordered pair, you're still going to have that same values. Yeah.
So the x, that's just the order.
Yep. And that's kind of the big giveaway here. As you start to work through these, that's how the ordered pairs work. You still don't know what your R value is sometimes, but as you start on quadrantals, it goes cosine sine. And you still have to figure out, you know, cosine squared plus sine squared equals 1. After all this time. Because if you think about, as you start building it through, on our unit circle, as we start to get to it, our radius is always going to be 1. Adjacent side quantity squared plus the vertical side quantity squared is always going to equal 1 as we build it out. Always. This is kind of a big deal. This comes up huge after we get back to the string graph.
Sorry that they're not here with this.
I know. I'm telling you, this is of all the beginning of units to have to miss out a lot of. This is kind of important because the whole idea of this whole oscillation between ordered pairs. Yes, I use the word oscillation. 0, 1, 0, 0, 1, -1, 0, and 0, -1. As you go around a circle, you start at your cosine value starts where? Where's cosine start? Starts at 1. Then where does it go to? 0, -1. Back to 0. And then eventually back to 1. There's a cosine graph. Where does sine start? 0. Goes to 1. Goes back to 0. Goes to negative 1. Goes back to 0. There's a sine graph. Aren't these two graphs the same graph, just shifted? Yeah. Tangent. If you start with tangent, what's 0 divided by 1? 0. So a tangent graph is at 0. Here it'd be undefined. At 1, it's undefined. Here it's back to 0. Here it's back to negative 1, which is undefined. So what we do is we graph tangent in between. Somewhere in between,
Yeah, because it goes kind of like
somewhere in between, what degree measure has a tangent has the same on both sides? 45. Because the tangent of 45 is always 1. The tangent of negative 45 would be negative 1. So tangent does this. Because of all of that. Yes, ma'am?
So for what we're swing, so depending on the quadrant and graph, that'll give you your x bar, and then the r is just always.
Pythagorean theorem. Well, it depends. If they give you your ordered pairs, you still have to find the r, because then it can vary itself out.
So
What's
what we did first.
yeah. This is getting ahead of ourselves into what we're going to look at more tomorrow.
Good.
I had it posted on the calendar what I wanted you guys to do today. I added in a couple of problems after I looked at it during the second hour with those guys too, so it's not like they didn't know about it. It's 26 through 44. I think I already did number 26. The first group of them is what we did in the very beginning. Write out the 6 trig functions given a specific ordered pair. You'll have to do some simplifying of radicals, nothing too crazy. The last 8 questions are finding reference angles. They're going to be larger degree, both in degrees and in radians. What I'd like you to do is find your reference angles, how far it bounces off your x-axis, because we can get, I'm pretty sure you guys are okay at reference angles so far, but it's just a little bit more practice on it because that's how everything works, and it's all via a reference angle. If we're really good at those, trig is pretty quick. Dealio?
Yep, sure.
Trig is fun. Because it all comes back together. It's why all this stuff works. It's why you need to figure out how far apart airplanes are to move it to different places.
Sorry about that.